Welcome to the Deep Dive, the show where we really try to get our heads around complex topics, unpack them, and arm you with the insights you need to be genuinely well-informed.
Hmm.
Today, we're plunging into a field that's, well, it's so mind-bending, it apparently even gave Albert Einstein pause.
Yeah, it really did.
Yet, it's right on the cusp of radically reshaping, well, pretty much everything, from how we compute to how we understand the universe itself.
That's right. We're diving into quantum information science, or QIS, and our mission here really is to cut through the hype, cut through the jargon, and give you a clear picture of this quantum frontier.
Okay.
We'll be digging into sources like the 2024 Quantum Information Science Applications Roadmap and other cutting-edge research. We want to explore the three main pillars: quantum computing, quantum sensing, and quantum networking.
So the goal for you listening is basically a shortcut. We want to give you the surprising facts, the aha moments, and help you understand what's real, what might be coming next, and frankly, why it matters.
Exactly. Let's unpack it.
All right, so to really get quantum, we need to start with the basics, the language it speaks.
Right. And at the very heart of it all is the qubit. Now, a classical computer bit, that's simple enough. It's a 0 or 1. That's it.
Binary. Yeah.
But a qubit, it can exist in what we call a superposition.
Okay, superposition. What does that actually mean in practice?
It means it can be both 0 and 1 at the same time, simultaneously.
Okay, that's where things start getting weird, isn't it? Because that's not just like a small step up. It's a huge leap in how much information you can store.
Oh, monumental. I mean, to give you a sense of scale, imagine a system with just 300 qubits.
Okay, 300 doesn't sound like that much compared to billions of transistors.
Right. But theoretically, those 300 qubits could hold more information, more distinct states, than the estimated number of atoms in the entire observable universe.
Wow. Okay, that scale is just hard to comprehend.
It really is. And what's maybe even stranger is that these qubits, they don't just exist on their own. They can become linked through this phenomenon called entanglement.
Ah, yes, entanglement. This is the spooky action at a distance thing, right?
That's the one. Einstein's famous and somewhat skeptical description. It means two or more quantum particles become sort of intrinsically connected. Their fates are tied together no matter how far apart they are. You measure one, you instantly know something about the other. Instantly.
Spooky indeed. But it's not just a theory, is it? Didn't this just win a Nobel Prize?
Exactly. Just recently, in 2022, Elaine Aspect, John Clauser, and Anton Zeilinger won the Physics Nobel for their experiments. They used entangled photons, tested it rigorously, and basically proved Einstein's spooky action is very, very real. It really happened.
So these quantum rules, superposition, entanglement, they're just fundamentally different from our everyday classical rules.
Completely different playbook. For instance, you've got the no cloning theorem.
No cloning.
Right. It states you cannot make a perfect copy of an unknown quantum state. Think about it. We copy classical information all the time, perfectly. Files, music, whatever.
Yeah, copy-paste.
Can't do that with an unknown quantum state. It's physically impossible.
Okay, so no quantum Xerox machines. That immediately sounds useful for security.
Definitely. And tied into that is another key rule: measurement disturbance.
Measurement disturbance, meaning just looking at it changes it.
Precisely. The very act of observing or measuring a quantum state inevitably alters it. Now, classically, that might sound like a problem, an observer effect we try to minimize.
Right.
But in quantum communication, it's actually a huge advantage. It means if someone tries to eavesdrop on a quantum signal,
They change it.
they change it. They leave an undeniable trace. It's like a built-in tamper-evident seal. The moment someone tries to listen in, the system knows.
Wow. So the act of spying becomes its own alarm system?
Yeah.
That's a really neat twist. What about other weird quantum rules, like Heisenberg's uncertainty principle? Does that play a role here?
It does. It sets a fundamental limit. You can't simultaneously know certain pairs of properties of a quantum particle with perfect accuracy, like position and momentum.
Yeah.
The more precisely you know one, the less precisely you know the other.
Okay.
Just a fundamental property of nature. And all these counterintuitive rules, superposition, entanglement, no cloning, measurement disturbance, uncertainty, they all highlight what we call the quantum engineering challenge.
Right, because working with this stuff must be incredibly difficult.
Immensely. We're talking about controlling systems at the atomic, even subatomic level.
Mm.
They're incredibly delicate, extremely sensitive to noise, vibrations, temperature fluctuations, any kind of external interference. It demands extraordinary precision.
Okay, so we have this new quantum alphabet, these really strange but powerful rules. Now let's talk about how we're actually trying to use them. the applications. You mentioned three pillars.
That's right. We can broadly categorize the applications into three main areas: quantum computing, quantum sensing, and quantum networking.
Let's start with computing. The promise here sounds enormous, solving problems even our best supercomputers can't touch, even with all the advances in AI and machine learning.
That's the core idea. Quantum computers aren't just about being faster for everything. They're about tackling specific types of problems that are fundamentally intractable for classical machines, problems where the complexity just explodes beyond classical capabilities.
Okay, give us some examples. What kind of intractable problems are we talking about?
Well, think about understanding the universe at its most fundamental level.
Hmm.
One really ambitious goal is simulating the strong force.
The force holding atomic nuclei together.
Exactly. Quantum chromodynamics, the theory describing how quarks and gluons interact to form particles like protons and neutrons. Simulating this accurately is critical for understanding things like the early universe, how matter formed.
Right.
But the number of possible states involved is just astronomically large, unimaginably large. Classical computers simply choke on it. A quantum computer, however, speaks the same language. It could potentially model these dynamics directly.
So, probing the very structure of matter and the universe's beginnings, that's profound. What about applications maybe a bit closer to our daily lives?
Absolutely. In chemistry and material science, the potential is frankly revolutionary. Consider the Haber-Bosch process for making ammonia, essential for fertilizer.
Yeah, feeds billions but uses huge amounts of energy.
Exactly. About 2% of global energy consumption, roughly. Quantum computers could potentially help us discover new catalysts or alternative pathways that are far more energy efficient.
That alone would be a massive win.
Huge. And, more broadly, they could allow for simulations of molecules and materials with unprecedented accuracy, without the shortcuts and approximations classical methods often need. This means designing new drugs more effectively, discovering materials with exotic properties, superconductors, better batteries, you name it.
So breakthroughs in energy, medicine, materials. What about other areas of science?
Oh yeah, it enhances scientific computing across the board. Think plasma physics for fusion energy, fluid dynamics for designing more efficient aircraft, structural mechanics, astrophysics. Many fields rely on solving complex systems of equations.
Right, like linear algebra problems.
Precisely. And there are early quantum algorithms like the HHL algorithm Haro-Hasidim-Lloyd that specifically target solving huge systems of linear equations exponentially faster than classical methods. That hints at the kind of speedups we might see.
Okay. And beyond science, you mentioned optimization.
Yes, optimization is another key area. Think about managing complex systems. Global supply chains, shipping routes, electrical power grids, financial modeling. These often involve finding the best solution out of a mind-boggling number of possibilities.
The traveling salesman problem on steroids?
Kinda, yeah.
Yeah.
As problems get bigger, classical solvers just grind to a halt. Quantum computers, using principles like quantum annealing or variational algorithms, could potentially find better solutions much more efficiently.
This all sounds incredible. The potential is clearly there. But what about the actual machines? Where are we right now? Are these things running complex simulations today?
We're currently in what's often called the NISQ era,
A nice cue.
noisy intermediate scale quantum. So the quantum computers we have today are intermediate scale, meaning they have a decent number of qubits, maybe tens to hundreds, sometimes even over 1,000 now.
Okay.
But they're also noisy. Those quantum states are still very fragile, prone to errors caused by environmental interference. This limits the complexity of the calculations, the depth of the quantum circuits they can run reliably.
So promising, but still prone to errors. What kinds of hardware are people building? Are there different approaches?
Oh, many different approaches. It's a very active area of research and development. You have qubits based on superconducting circuits, which companies like Google and IBM use. There are trapped ions manipulated with lasers, neutral atoms held in optical tweezers, quantum dots in semiconductors, even topological qubits, though they're further out. Each platform has its own pros and cons regarding stability, connectivity, speed.
It sounds like a real race to find the best approach. I imagine governments are heavily involved in funding this.
Absolutely. The U.S. Department of Energy, the DOE, for example, has made significant investments through its national QIS research centers.
Right, you mentioned names like C2QA, QNNXT.
Exactly. C2QA, QNXT, QSA, SQMS. These centers bring together national labs, universities, and industry. They're building test beds, providing access to researchers. For instance, the QSA Center Quantum Systems Accelerator recently built a quantum simulator using 256 neutral atoms. That's a significant scale for that platform.
Yeah.
And SQMS, the Superconducting Quantum Materials and Systems Center, they have this quantum garage where they're building and testing advanced superconducting quantum processors, focusing on improving the materials themselves to reduce noise.
That seems crucial, tackling the noise problem head on. So, what are the biggest hurdles still? Is it just noise and errors?
Noise and error correction are definitely the biggest ones right now. Even tiny imperfections in materials or fabrication can kill quantum performance. So we need exquisite control, better material science, advanced manufacturing, and then we need clever ways to correct the errors that inevitably happen.
Right.
The field is sort of pursuing a dual path. On one track, pushing hard towards large-scale, fault-tolerant quantum computers. These would have enough qubits and sophisticated enough error correction built in that they could run complex algorithms reliably for a long time.
The ultimate goal.
The ultimate goal. But that's likely still a ways off. So the other track is finding practical applications for the NISQ devices we have now and the improved ones coming soon. Even noisy machines might offer advantages for certain scientific or optimization problems.
Okay, makes sense. So what's the timeline look like? What can we realistically expect, say, in the next 5 years?
In the next 5 years, I think we can expect to see maybe the first small, error-corrected quantum computers emerge. Not fully fault-tolerant yet, but capable of running algorithms with significantly reduced noise. And alongside that, we'll likely see clearer demonstrations of quantum advantage.
Quantum advantage, meaning?
Meaning performing a specific, useful computation, likely a scientific one that is demonstrably beyond the reach of any classical supercomputer, not just a contrived benchmark, but a real problem.
Okay, that would be a major milestone. And longer term, say 5–10 years out.
Looking further out, say 5–10 years and beyond, a big focus will be on building the architectural components needed for truly large systems. Things like quantum interconnects.
Like quantum networking within a computer.
Essentially, yes. Ways to reliably link different quantum processing units together, maybe even across different physical locations within a data center. This is crucial for scaling up, for building modular systems that can grow much larger than a single monolithic chip might allow.
Okay, that leads us nicely into the other pillars. Let's switch gears from computation to sensing, quantum sensing. You said it offers unprecedented precision. How does that work?
Right. Quantum sensing is all about using quantum phenomena again, things like superposition and entanglement, to make measurements with sensitivity or precision that fundamentally surpasses what's possible with classical sensors. It's about beating the so-called standard quantum limit.
Standard quantum limit, like a classical noise floor.
Sort of. It's a fundamental limit based on classical statistics and uncorrelated particles. Quantum sensors can use correlations like entanglement or techniques like squeezing quantum noise.
Squeezing noise, what does that mean?
Imagine the uncertainty in a measurement is like a balloon. You can't make the balloon smaller overall due to fundamental quantum limits, but you can squeeze it in one direction.
Okay.
So you might increase the uncertainty in, say, the phase of a light field, but dramatically decrease the uncertainty in its amplitude. If amplitude is what you care about measuring, you've effectively pushed the noise out of the way and made your measurement much sharper.
I see. That's a great analogy, squeezing the noise into a dimension you don't care about. So what can these super precise sensors actually do for us? What are the killer apps?
Well, one huge area is ultra-precise timekeeping. Atomic clocks, which are essentially quantum sensors, are already incredible. The best ones now have errors equivalent to less than half a second over the entire age of the universe.
That's just mind-boggling precision.
It is. And this enables really fundamental tests of physics, like checking Einstein's theory of general relativity with extreme accuracy. It's also crucial for things like global clock synchronization, improving GPS, enabling next-generation communication networks, even synchronizing financial transactions.
Okay, so better clocks. What else?
They can also act as incredibly sensitive microscopic probes. Imagine sensors with high spatial resolution that can probe materials, chemical reactions, even biological samples down to the level of single molecules or atoms.
Like MRI, but way, way more detail.
Potentially, yes. For things like biomedical diagnostics, designing drugs, understanding chemical processes at the most fundamental level. And some types of qubits using sensors like nitrogen vacancy centers in diamond are remarkably robust.
Robust how?
They can operate in really challenging environments, high temperatures, high pressures near plasmas, underground, even in space places where traditional sensitive equipment would just fail.
Okay, that opens up a lot of possibilities. Are they being used to look for, like, new physics, cosmic mysteries?
Absolutely. Quantum sensors are at the forefront of the search for elusive dark matter particles, things like axions or WIMPs. They're also used to test if fundamental constants of nature are truly constant, or if they might change subtly over time.
Wow.
And there's a lot of interest in creating networks of quantum sensors. Linking them together could dramatically improve their sensitivity for these kinds of searches, or for applications like geodesy.
Geodesy, measuring the Earth.
Yeah. For example, quantum gradiometer sensors that measure tiny changes in gravity gradients could potentially monitor things like millimeters of change in global ocean levels or glacier melt year over year. They can do this by canceling out common mode noise that affects the whole sensor system, equally allowing them to see incredibly subtle gravitational shifts.
That's incredible. Truly next-level monitoring of our planet. So what's the path forward here? How do we get more of these amazing sensors?
It really requires continued broad collaboration. You need physicists, material scientists, engineers working across all the different platforms, cold atoms, trapped ions, superconducting circuits, molecular systems. The goal is always to push performance further beyond that standard quantum limit, unlocking even greater precision and opening up new scientific frontiers.
Okay, so we've covered computation and sensing. Now let's move to the third pillar, quantum networking and communication. The idea of a quantum internet sounds like pure sci-fi. What's the vision here?
The vision is essentially a network that connects quantum devices, computers, sensors, not just by exchanging classical data, but by distributing quantum states, particularly entanglement, over long distances.
So sending qubits and entanglement through fibers or space?
Exactly. Through fiber optic cables like our current internet, but also potentially through free space links, maybe using satellites. The idea is that entanglement could become a kind of generic resource available on demand across the network, enabling all sorts of new capabilities.
That sounds like a massive undertaking. Is there actual market interest in this? Is it moving beyond just research labs?
Oh, definitely. Market research projects significant growth. One report sees the quantum communication market expanding from around $1.37 billion in 2025 to nearly $14 billion by 2034.
Wow, that's a big jump, almost 30% growth per year.
Yeah, a compound annual growth rate over 29%. And what's driving it? A lot of it is hardware innovation that's projected to be over 60% of the revenue. And a major application area pushing this is national defense, accounting for something like 43% of the income.
Okay, so defense and security are big drivers.
Right.
That makes sense, given what you said earlier about quantum properties. How exactly do quantum networks boost security? This sounds like the hero application.
It really is often framed that way. The flagship application is quantum key distribution, or QKD.
Right, QKD. How does it work again?
It uses those fundamental quantum laws we talked about,
Mm-hmm.
particularly the no cloning theorem and measurement disturbance. If two parties want to establish a secret cryptographic key, they can exchange qubits. If an eavesdropper, let's call her Eve, tries to intercept and measure those qubits to learn the key.
She inevitably disturbs them.
Exactly. Her measurement leaves detectable errors in the transmission. The legitimate users, Alice and Bob, can check for these errors. If they see too many, they know someone was listening in, and they discard the key and start over.
So you have mathematically provable security based on the laws of physics, not just assumptions about computational difficulty.
Precisely. You know instantly if your key exchange has been compromised.
Is this being used now? Is it practical?
Yes, it's moving beyond the lab. QKD systems are commercially available. Governments are using it for secure communication, for example. It's been used to help secure parts of the election process in Switzerland. Industries like lotteries are using related quantum random number generators to ensure true randomness, which is surprisingly hard to achieve classically.
Interesting. But I've also heard a lot about post-quantum cryptography, PQC. How does that fit in? Is it competing with QKD?
That's a great question. They're often discussed together, but they're actually quite different and more complementary than competing.
Mm-hmm.
PQC is a software-based approach.
Software, okay. Not hardware like QKD.
Right. PQC relies on developing new classical encryption algorithms based on mathematical problems that are believed to be hard for both classical and quantum computers to solve. Think complex problems in areas like lattice-based cryptography or hash-based signatures.
Believed to be hard, so not quite the same physics-based guarantee as QKD.
Not quite the same fundamental guarantee, but based on strong mathematical conjectures. The big advantage of PQC is that it's software. It can potentially be deployed on our existing internet infrastructure, maybe with just software updates.
Much easier integration.
Potentially, yes. NIST, the U.S. National Institute of Standards and Technology, is in the final stages of standardizing the first set of PQC algorithms. And major tech companies, Google, Apple, IBM, Microsoft, are already starting to integrate PQC into their products, browsers, internal communications, preparing for the future.
So QKD offers physics-based security for key exchange, while PQC offers quantum-resistant algorithms for general encryption and signatures, potentially easier to deploy widely. Now, you mentioned security as a driver. What's the actual threat, the villain in this story?
The villain is often described as the store now, decrypt later threat, or sometimes harvest now, decrypt later.
Okay, what does that mean?
It means that adversaries, maybe nation-states, maybe sophisticated criminal groups, could be intercepting and storing large amounts of encrypted data today. Data protected by current standards like RSA or elliptic curve cryptography.
Stuff we rely on for banking, secure websites, everything.
Exactly. Now, this data is safe today because breaking that encryption is computationally infeasible for current computers.
Right.
But the fear is that once large-scale, fault-tolerant quantum computers become available,
They could break current encryption.
they could potentially break RSA and similar schemes relatively easily, maybe in minutes or seconds, using algorithms like Shor's algorithm. So all that data harvested today could be decrypted later, potentially years from now. Sensitive government secrets, corporate IP, personal data suddenly exposed.
That's genuinely alarming. It creates a real urgency to adopt quantum-safe solutions like QKD and PQC now, even if powerful quantum computers are years away.
That's precisely the argument. We need to protect data that needs to remain secure for the long term.
Okay, so security is huge. But quantum networks aren't just about security, right?
No.
What else can they do? You mentioned linking sensors earlier.
Yes, distributed quantum sensing is another major application. By sharing entanglement across a network of sensors, you can correlate their measurements in ways that dramatically improve sensitivity or resolution, like linking optical telescopes together across continents to create effectively a much larger telescope, enabling incredibly high-resolution astronomical imaging, or synchronizing atomic clocks globally with even greater precision than currently possible for those fundamental physics tests or improved navigation.
Okay. And what about linking quantum computers themselves, distributed quantum computing?
Absolutely. We already know the benefits of networked systems in classical computing modularity, allowing you to build large systems from smaller parts. Robustness, so if one part fails, the system might still function. Scalability.
Right.
Those same advantages apply to quantum computing. Building one enormous perfect quantum computer is incredibly hard. But maybe we can build smaller, powerful quantum modules and link them together using quantum network connections.
How would that work? How do you send quantum computations across a link?
There are techniques being developed like quantum state teleportation, which, despite the sci-fi name, doesn't move matter, but transfers a quantum state from one qubit to another distant qubit using entanglement and classical communication, or even gate teleportation, where you effectively perform a quantum operation on a remote qubit.
So you can build bigger quantum computers by networking smaller ones using these teleportation tricks. That's really clever. Is there anything else these networks enable?
One really intriguing possibility is called blind quantum computation.
Blind computation.
Yeah. Imagine you have a relatively simple quantum device, but you want to perform a really complex quantum calculation that only a large, powerful quantum server can handle. Blind quantum computation protocols could allow you to delegate your computation to that remote server,
Okay.
while keeping your input data, the algorithm you're running, and even the result completely private from the server itself. The server performs the calculation without knowing what it's actually computing.
Wait, really? You can use someone else's quantum computer without them knowing what you're doing. That's incredible for privacy and security.
It's a fascinating prospect, yeah.
Yeah.
Leveraging powerful quantum resources securely.
Okay, this quantum internet vision is powerful security, sensing, distributed computing, blind computation. But it sounds like it needs some pretty advanced underlying technology. What are the key building blocks?
You're right, it requires several key enabling technologies that are still under intense development. Quantum memories are absolutely crucial.
Memories to store qubits.
Exactly. Because quantum information is so fragile, and because things like entanglement distribution often rely on synchronization, waiting for signal to arrive from different places, you need ways to reliably store quantum states for short periods without them decohering, especially important for quantum repeaters.
Okay, and are we making progress on memories?
Yes, there are breakthroughs happening. For example, researchers recently demonstrated the ability to produce, store, and then retrieve quantum information encoded in photons at standard telecommunications wavelengths, the wavelengths used in today's fiber optic networks. That's a really critical step for compatibility.
That sounds huge. And you mentioned quantum repeaters. Why are they needed? Can't you just amplify a quantum signal like we do with classical signals?
Ah, good point. No, you can't because of the no-cloning theorem. You can't just make copies of a quantum state to boost it. And quantum signals, especially single photons, are incredibly lossy in optical fibers. They get absorbed or scattered quite quickly.
So the signal dies out over distance.
Right, much faster than classical signals. So instead of amplifiers, a quantum network needs quantum repeaters. These are complex devices that work differently. They typically involve distributing entanglement over shorter segments of the link and then performing a process called entanglement swapping at the repeater station to extend the entanglement over the full distance.
Entanglement swapping. Sounds complicated.
It is. Repeaters are often categorized into generations. First-generation repeaters focus on heralded entanglement generation and purification. Later generations might incorporate more advanced quantum error correction techniques to combat noise and loss more effectively. They are a major research challenge.
Okay. Memories, repeaters. What else?
We also need quantum transducers.
Transducers, like converters.
Exactly. Different quantum technologies often work best with different physical systems. For example, superconducting qubits operate using microwave signals, but for long-distance communication, optical photons traveling in fiber are much better. A transducer is a device that can coherently convert a quantum state from one form to another, say microwave to optical, without destroying the quantum information. This is vital for connecting different types of quantum devices together seamlessly.
Right, making everything compatible. What about the communication channels themselves? What are the main problems there?
Two main enemies: attenuation and decoherence. Attenuation is just the loss of signal photons getting absorbed or scattered in the fiber. And as I said, it's much worse for single photons than for bright classical laser pulses.
Okay, loss.
Decoherence is the loss of the quantum nature, the quantumness of the state due to interaction with the environment, with noise. The qubit state essentially degrades back towards a classical state. And noise is everywhere. Even just stray light from classical data channels running in the same fiber bundle through effects like Raman scattering can completely swamp the incredibly faint single-photon quantum signals.
Like trying to hear a whisper during a rock concert.
Exactly.
Yeah.
That's a huge practical challenge for deploying quantum channels alongside classical ones.
Given the loss in fiber, what about using satellites? Could that be a way around it?
Yes, satellite quantum links are a very promising alternative, especially for very long distances, like intercontinental links. While free space transmission also has losses, atmospheric absorption is much less of a problem than absorption in long stretches of fiber. For a link of, say, 1,200 kilometers, a satellite link could potentially be something like 15 orders of magnitude more efficient in terms of photon survival rate compared to fiber.
15 orders of magnitude? Wow.
Yeah. So organizations like NASA are actively exploring this. They have a concept called QIST.
Kediston.
It's a multi-phase project aiming to establish space-based quantum entanglement distribution. First between ground stations across the U.S., maybe up to 1,200 kilometers apart, and eventually between continents, targeting distances like 6,000 kilometers. The goal is to have intercontinental demonstrations perhaps by 2030.
So a quantum network backbone in space, that's ambitious. Finally, what about the overall structure, the architecture of these networks? Is anyone working on the quantum equivalent of like the Internet Protocol Suite to TCP/IP?
Absolutely. Researchers are developing conceptual models for quantum internet protocol stacks, defining the different layers needed for everything from the physical transmission of qubits to routing entanglement and running applications. People like Stephanie Weiner and colleagues have published influential models.
Okay.
And there's a lot of work using simulation tool software like NetSquid or Simulacoron to design and test network protocols before building expensive hardware.
Plus, there are various experimental test beds around the world, like the early DARPA Quantum Network, the Tokyo QKD Network, and many university and national lab collaborations where researchers are actually building and connecting small-scale quantum network nodes to learn how to make this work in practice.
Okay, it's clear this whole field of quantum information science is moving fast with incredible potential. But pulling it all together, what are the biggest hurdles that still remain across the board? I think the overarching theme, really, is still the engineering challenge. Across computing, sensing, and networking, we need substantial, continued R&D. We need more fundamental scientific discovery, certainly, but also massive innovation in sort of the supporting technologies.
Like what?
Things like advanced packaging to protect delicate quantum devices, developing new materials with better quantum properties, creating more efficient and lower noise optical modulators, cryogenics, control electronics, all the classical engineering that needs to surround and enable the quantum core.
So it really requires this deep interdisciplinary effort. It's not just quantum physicists working in isolation.
Absolutely not. It demands broad, ambitious, collaborative work spanning classical engineering disciplines and fundamental quantum science. And scalability is another huge, persistent challenge.
Scalability in what sense?
In quantum computing, it's about how we get from today's NISQ devices to truly large-scale fault-tolerant systems, whether by building bigger single processors or effectively networking many smaller ones. In quantum networking, it's about moving from small, proof-of-concept networks in labs to robust, city-scale, and eventually global networks. That's a massive leap in complexity and reliability.
And how do these future quantum systems live alongside our existing classical infrastructure? You mentioned the noise problem.
Right, that coexistence is a major practical hurdle, especially for networks. Trying to run fragile single-photon quantum signals in the same fiber optic cables as powerful classical laser signals is incredibly difficult due to noise like that Raman scattering.
The whisper in the rock concert again.
Exactly. And the synchronization requirements for quantum networks, especially for things like entanglement swapping and repeaters, are often far more demanding, needing much tighter timing precision than typical classical networks. It's a complex integration challenge.
So definitely not straightforward. It sounds like this is a journey with quite a few bumps still ahead.
For sure, it's a constantly evolving field. The timelines definitely carry uncertainty, things might take longer than hoped, or new breakthroughs could accelerate progress unexpectedly. But the fundamental promise, the potential for genuine revolution across science and technology, is undeniable.
We have covered a lot of ground today, from the frankly bizarre rules of quantum mechanics, things like superposition, entanglement, the spooky action, to the really tangible applications starting to emerge. Powerful quantum computers tackling impossible problems, sensors with unbelievable precision, and networks promising unbreakable security.
It's really about harnessing these fundamental counterintuitive aspects of nature to do completely new things with information.
So thinking about all this, what really stands out to you? How might these quantum leaps truly redefine how we think about information, how we handle it, secure it, use it globally? For me, I keep coming back to that idea of measurement disturbance being the key to security, or just the sheer scale of computation hidden in just a few hundred qubits, enough to simulate the universe's beginnings. It's staggering.
It absolutely is staggering, and maybe the most profound shift is moving from just observing the quantum world to actively engineering it. Imagine a future where we're not just limited by the classical rules we're used to, but we can leverage the full, strange, powerful rules of quantum mechanics, the rules the universe actually runs on to build technologies and solve problems in entirely new ways.
That leads to a great final thought, doesn't it? What new problems will we solve? What new discoveries will we make when we truly learn to compute like nature? Something for all of us to ponder.